Hello everyone. Welcome to the second video for 1.1. Uh, Hopefully everyone's been watching the video series to know that these four formulas hold. So I'll erase them off, uh, and we'll talk about more roots, and specifically we have to know some qualities about roots that aren't really given on this sheet right here. Um, so I'll just go over them. So one generic quality that they want you to know is this, that the sum of roots for any like polynomial, when you square it, it's basically going to be something like alpha plus beta plus gamma plus so on, right? Times, alpha plus beta plus gamma, the whole thing, right? Itself, because it's squared. And pretty much when you do that, what happens is you get alpha squared plus beta squared plus gamma squared, right? So alpha squared plus beta squared plus gamma squared, and so on. So the sum of the squares of each of the roots plus, and then you get alpha times beta plus beta times alpha, right? And you repeat, you get alpha times gamma plus gamma times alpha plus beta times gamma plus gamma times beta, right? So you basically get 2 times alpha beta sum, right? So I'll just erase this really quick. Okay, but pretty much you just get plus 2 times alpha beta plus beta gamma plus alpha gamma, gamma plus so on, right? Therefore, it can be simplified for general application. The sum of the roots squared is equal to the sum of the roots squared plus 2 times the sum of a linear combination of the two roots added together. So pretty much it just means, like, you could imagine it for quadratics. So you have alpha plus beta whole squared, so you just apply a squared plus b squared plus 2ab, which is the same thing as what this is saying. So yeah, so this applies, so this is what you need to know. So please remember this. Another thing you need to know is recurrence relations. So I'll just go over that right now. Pretty much, hopefully you guys already have an idea for what recurrence relationships are, but I'll just quickly go over what they are. So in mathematics, whenever you want to define a series or like a relationship, for example, you have un plus 1 equals 3un plus 2, right? You want to be able to define a proceeding term with a preceding term, and you have to have a base case, which basically means that once you get down to a certain n value, you want to be able to actually plug in a number for it. So if you want to find out u3 for this, that's just equal to 3u2, right, from this equation right here, plus 2. u2, which you plug n equals 1 here, equals 3u1 plus 2. And from our base case, we have 3 times 1 plus 2, which is 5. When we plug this back in here, is 3 times 5 plus 2, which is 17. So that's just a general introduction to recurrence relationships. Pretty much, proceeding terms are described with preceding terms. Okay. So pretty much similarly, we could use that concept with roots. So in general, we denote Sn equals sum of alpha to the n, not big bracket alpha. It's not the same thing as this. That's completely different. This is different, okay? So whenever you see a question that asks you whenever you see a question that asks you oops, 1 second, sorry for this. Yeah, so whenever you see a question that asks you alpha squared plus beta squared, find this for a quadratic. Well, from our previous part where we had this formula, sum of alpha whole squared is just equal to sum of alpha squared plus 2 times sum of alpha beta, right? We had this in the just what I explained. So you just make this the subject of the formula, and you basically get sum of alpha whole square minus 2 times sum of alpha beta, right? Easy enough. But when you have something like alpha to the 4 plus beta to the 4, or alpha to the 5 plus beta to the 5, this becomes a lot harder, right? Um, so pretty much that's why we use recurrence relations, especially for like cortex, where they're extremely helpful. So pretty much whenever we're asked to, whenever you're given an equation, let's say you're given the equation x squared plus 5x plus 7. Let's consider x squared plus 5x plus 7 the quadratic equals 0, right? So we have two roots for this, alpha and beta, right? And let's say we want to find alpha squared plus beta squared, right? So we want to find S2 right here. Thing is, we already know that alpha and beta each apply to this formula, right? That's why they're called the roots or the solutions. So we know that this is true equals 0. And we also know that this is true, right? Because each of them apply. And of course, they're interchangeable roots. But pretty much what you do now is just add both of these equations up. And now what you get is alpha squared plus beta squared, right? Plus 5 times alpha plus beta, plus 2 times 7, which is 14, equals 0, right? This means that using our summation, the recurrence relation, we could say that S2, which is this thing right here, S2 equals negative 14 minus 5 times alpha plus beta, right? And alpha plus beta we could just find as S1, right? S1 is just alpha to the 1 plus beta to the 1. And then this could just be found by our initial formula, negative b by a, which is just equal to negative 5 in our case. Since this is equal to negative 5, we can find a value for S2. So we get, I'll put more space here. So pretty much you could probably do the calculation in your head. But pretty much we have, we had S2 equals negative 14 minus 5 S1, if I remember correctly. And pretty much this can be solved because we have this is equal to negative 5, S1 equal to negative 5. So S2 equals negative 14 plus 25, plugging this into the equation. And then we just get 11. So that's our answer. 11 is going to be our answer. That's how you work that out. Thing is, with higher powers is if you want S3, right, for this quadratic equation, or alpha cube plus beta cube, you could just use the same thing again, right? So here, where you have x squared plus 5x plus 7, you just multiply x with everything else. So this gives you something like that, which implies that x cubed plus 5x squared plus 7x equals 0. This implies that S3, right, because alpha cubed plus beta cubed plus gamma cubed, we're adding them together, right, plus 5 times S2, right, plus 7. So the coefficients you notice, so there's 1 here, there's 5 here, and there's 7 here. They remain the same. S1 equals 0, right? You get it? So pretty much you have S3 equals negative 5S2, right, minus 7S1. And from our previous calculations, we had S1 equals negative 5 and S2 equals 11. So we could plug that in here just to, in our calculators, and we'll get negative 55 plus 35, which is equal to negative 20. So that would be our answer there. S3 equals negative 20. And we've just found that huge, something that we would find difficult, ideally. And we've used recurrence relations to our advantage. Now, if we have some other stuff, like this applies with negative numbers as well. So basically, if we have something like find the sum of 1 by alpha cubed, right? Or alpha squared, let's say, alpha squared. 1 by alpha squared, right? If we have something like this for a quadratic, right? Then, and the quadratic, let's just take it as the same thing. X squared plus 5x plus 7 equals 0, right? If we have it for a quadratic, then we just know that dividing by x squared would help us here, because we want s to the -2 here, s to the -1 here, and s 0 or just 1 right here. Okay, so dividing by x squared, we get 1 plus 5 by x plus 7 by x squared equals 0, right? Remember, there's two roots, so we're multiplying 1 by 2. So you get 2 plus 5s to the -1 plus 7s to the -2 equals 0, right? And we find s to the -1 to be, well, you could use, again, recurrence relation here and divide by x, or you could just use the fact that it's equal to 1 by lambda, 1 by alpha times plus 1 by beta, which is just alpha plus beta by alpha beta after you cross multiply. And you can see that alpha beta is just equal to this thing right here, negative b by a, c by a, c by a, so that's 7. And alpha plus beta is -5, so -5 by 7 would be what we use for s is equal to s of -1. And once we get that, we basically get s of -2, our original equation here, is just equal to 1 by 7, because we have the 7 as the coefficient here, right? Times -5, because we have the coefficient -5 here, times -5 by 7 from the value of s is -1 minus 2, right? And plugging this into your calculator, let's see, you'll get 11 by 49 should be your answer. Not sure though, but yep. That's sort of how you use recurrence relations to your advantage. Remember that when you have another equation like x to the 4 plus 5x cubed plus 2x squared plus 3x plus 1, you could use recurrence equals to 0. You could use recurrence relations right here. And you could say s4, right, plus 5s3 plus 2s2 plus 3s1 plus, remember, 4, because there's 4 roots, remember that, equals 0, right? You could use that. But the thing is, before you do that, you need to calculate s3, right? And s2. So you get, from this same equation, divide by s, and you get s3 plus 5s2 plus 2s1 plus, since the 3 is being divided by x, and then multiplied by 4, you get 12, plus s of -1 equals to 0. And s of -1 is something you'd have to know for that. Ideally, in the question, you'd be given some of these values before, so you'd be given s -1 here, and s of 1, of course, from the equation you can derive. And then s of 2, you'll probably have to find with something like sum of alpha whole squared equals sum of alpha squared plus 2 sum of alpha beta. You just find this term right here to get s2. And then you find s3, and then you plug that in here, you plug s2 in here, you plug s1 in here, and then you solve for s4, and that should give you sum of alpha to the 4. That's what some long questions do. They could even ask for s to the -4. But remember one thing, that recurrence relations are something you can definitely use to your advantage when calculating sum of roots or sum of powers of roots. That's pretty much all I have for this video. In the next video, we'll be discussing this pointer right here. Use a substitution to obtain an equation whose roots are related in a simple way. I will basically be going over how to get a different equation using an equation we already know for particular values of roots. Right? Thank you.